In this video, we're going to discuss light, what it is, where it comes from, where it goes, and how it works. Now that might seem like a simple list, but we puzzled over it for eons, and we are still doing so today. What do we know about light? What can we define fairly well? And that'll eventually lead us into what we don't know about light. To start with, what is light? Light is energy. Light, photons, which is how we talk about the individual bits of light, photons are packets of energy. Now, they're not a particle. As we'll discuss later, light is a wave, but what its existence is just pure energy. There's no matter, there's no mass, it's just the energy itself. Light can be emitted by things, it radiates across the universe until it runs into something. It can be absorbed or re-emitted, it can be reflected, all sorts of things can happen. It is just energy. It's not potential, it's not kinetic, it's not thermal. It can be converted into all of those, but it is just light energy. Well, how do we discuss light? There's a couple ways. First and foremost, lambda is the wavelength. Nu, which sort of looks like a V but with a more curved front, this is the frequency. And speed. C is the speed of light. Specifically, speed of light in a vacuum. The speed of light is actually adjustable as it passes through things, gases, liquids. The effective speed changes. And so we tend to define c, the speed of light, as in a vacuum with nothing to obstruct it. Now, speed of light, just as an aside, has nothing to do with light. It is the maximum speed that anything can transfer through the universe. The fastest something can go from one point to another point in the universe. Well, there's a transmission, there's a travel. That fastest anything can go from one spot to another happens to be a certain speed, and light travels at that speed. It has nothing to do with light, it has to do with the universe. Light just can go that fast. Generally, this is about 3.00 times 10 to the 8th meters per second. Now you can find slightly more accurate values where it's 2.99 and so on, but this will be the general value we use. Rather convenient. The wavelength and the frequency change. If we think about a wave, the wavelength is the distance from one peak to the next peak. This is our lambda. And different waves can have different distances between their peaks. Well, if you set up a watching point and you had light travel at the speed of light, and you were to count every time a peak hit that top. So there's 1. There's 2. There's 3. So that took 1 second and 3 of the peaks could touch. Well, if I have a smaller wavelength, 1, 2, 3, 4, 5, 6, 7 touch before we reach the end. I made these two about the same length, so in theory they're traveling at the same speed if they both move forward, but one of them is just going to hit that green line more often. So as they travel that lower one, more peaks strike the line. The frequency, the number of times per second that it hits that line, is greater. The bottom one, we say, has a higher frequency. The top one has a lower frequency. Wavelength and frequency are inverse measurements of each other. The bigger the space between your peaks, the less peaks will pass that line as you move forward at the speed of light. The smaller distance between your peaks, the more peaks will pass that line as you move forward at the speed of light. And so wavelength and frequency are convenient opposites to each other. For light, we have an equation that will say the speed of light is always going to equal the frequency times the wavelength. Because the speed of light is constant, the other two adjust around the speed of light. So if we know the speed of light, let's talk about, say, blue light. A blue wavelength is on the order of 450 nanometers, which is a pretty small wavelength. This would be 450 times 10 to the minus 9 meters. So remember, a nano is 10 to the minus 9. 450 nanometers is 450 times 10 to the minus 9 meters, which means we can find the frequency. The frequency is the times per second. And so the value for it, we call that hertz. The per second is a hertz. Our frequency is going to be how many times per second. Divide and rearrange. What is our frequency of our blue light? So we divide 450 times 10 minus 9 over. What we'll find is that the frequency of blue light 6.67 times 10 to the 14 hertz. A lot of old documentation and old concepts in light chemistry dealt with frequency. Today, thanks to advancements in detection technology and a lot of things, we use wavelength far more often than we use frequency. It's just not as useful a tool anymore. We can actually discuss the size of the wavelength that the photons exist as, and our devices readily can determine those. And so most of our equations will focus more on wavelength, but frequency is still worked in. So it's important to see how we can calculate it and where it comes from. So where does light come from? Well, we'll go in much more detail as we get to orbitals. Light, as far as chemists are concerned, generally comes from electrons moving around an atom. And so I have some nucleus. There are some electrons around it. Light can hit those electrons. And when it does, it can bump those electrons further out, we say to higher orbitals. Well, electrons don't tend to stay in higher orbitals. If you can fall lower, like a rock on a hill, you can fall down. It's really hard to fall back up. It's really easy to fall down. There's always a favorable attraction pulling that electron back in. And so eventually that electron jumps in. But to do it, it has to give away energy. And so it gives away a photon. It gives off light. This is how lamps work. If you have fluorescent lamps and the like, this is how neon lights work. You excite electrons, and the transition, the energy to raise or lower electron, well, that energy has to go somewhere, and it's emitted as light, or is absorbed in order to originally raise the electron. And so the construction of our atoms, the construction of our molecules, all of that affects the electrons that make up the atom and the molecule. And so what colors you get, how you interact with light, all of that is dependent on the chemicals you are using. So we're going to see a lot more of that in our next video.